This is part 2 of how we can get our relay contacts to last much longer. As you can see here, some arcing happening. Over time, this will mess up your relay contacts to the point where they'll either weld together, so your device will never turn off, or so much material will be lost on the contacts themselves that they don't make an electrical connection, in which case your device doesn't turn on. So a little more dramatic example with this. That is exactly what we don't want to happen. So we're going to talk about how to minimize this arcing. So recap from part 1, a regular flyback diode is too slow. This opening of the actual contact is slow. So what we want is just a bidirectional TVS diode. The voltage, as long as you're not blowing other components because the voltage is too high, you're fine. So what's going on here is an unprotected relay. So if you're going to do this, then you need to overspec your relay, but we found it work that even overspecking quite a bit can cause failures, enough failures that it's unacceptable. So, but in plenty of circumstances, it will last forever, practically. So anyways, what I would recommend you do, if you already have this setup, is to actually measure it with a scope. Because once you put in the solution, which we're going to talk about, you have to scope it anyways. So at this point, we got to talk about safety a little bit. So if you're measuring AC with a probe, you need to make darn sure that your probes are going in the right place. If your ground lead goes to line voltage, not only will you blow the probe, potentially, but that's connected to earth ground, man. You're causing a short. You're going to screw up your oscilloscope and destroy it, potentially. So there are ways around that, but for this video, just be really sure your probe leads are where they need to be. Also, since you're going to have an inductive load, you're going to see voltages here in excess of 500 volts. So your regular probe leads cannot do that much. So you need to go get some probes that can do it. You know, attenuation value, 100x, that'll be fine. If you look at all these voltage maxes over here, this will be plenty. So just make sure you get the right stuff, and then you'll be good to go. Question I originally had when I was doing this was, I only do 10x scopes. Can my oscilloscope do 100x? Or I think what I used at work was 1000x. The answer is yes. You can configure your scope to do these higher ones. No big problem. I used a 30-year-old Tektronix scope. So that's another safety thing I do. Because there is a risk of going backwards with the leads and messing things up, I use a cheap 30-year-old Tektronix scope. One, I love them, but two, they're expendable. So now what we're going to do is talk about the actual solution of what to put on the leads here. So we're going to get rid of this, and we're going to get this bad boy over here. We're going to bring it over here, and we're going to connect everything. Like so. Okay. This right here is called an RC snubber. Gotta love these electrical people and how they name things. So I wish I could show you actual scope readings. Nobody seems to have published like anything practically. So without anything, you'll see 500 volts. With this setup here, it'll just go yeah for a while and just die out, which is exactly what we want. Okay, so what's our end goal here? Well, I got this from Henry Ott's EMC book, and basically we want two things. We want to keep contact voltage below 300 volts. So, but, you know, you may say, hey, I'm at 240 volt AC at the top of the sine wave. I am above 300. So am I screwed? No, you're not. So technically, you know, you're only above 300 for a little bit there. So you lost the battle for that little bit, but you can still win the war. Okay, and then we want to keep the initial rate of rise of the voltage to 1 volt per microsecond or less. I can tell you this setup, at least with the load that I have, works just fine. So that's another question others will have. Where do these come from? These values? Are you just pulling them out of your ass? Honestly, kind of. The internet seems to have settled on these values, 100 for sure. For there may be some variation here in the capacitor, maybe 0.1 microfarad. Since what I had at work was very inductive, they said, "Hey, try 0.22." So it worked. This is one time the internet is actually right. It's unbelievable, right? So now another question is there math you can do to get actual values? Yeah, sure, but you need to know just how inductive your load is. If it's like a motor or compressor, you won't be given those numbers. So it's you just got to try and then measure. So guess and measure. So as long as you fit these two, you should be good to go. Along with what we're already doing on the coil side, you'll be good. So laws of physics now. In order to get rid of an arc entirely, your voltage has to be like less than 12. And your current is like less than 3 and 400 milliamps. If you can meet those, no arcs, you're good. But yeah, that's not how real life works, man. So we can't stop an arc, but we can sure minimize it. So now we got our values set in, and we've got some criteria of what to look for. We got to talk about the components themselves, because you just can't pick what's going on willy-nilly. The compliance people will be on you. You'll never pass compliance. So let's talk about the components. We're going to start with the resistor here. So just a regular 100 ohm resistor. So what do we need? That's the question. Well, here, let me go back up on this spreadsheet here. This is Texas Instruments SLUP 421. Don't know what they're thinking. But the important part is that when it comes to AC, you got to be able to deal with transient over voltages. So what we are in is category 2. So it's just an outlet that's far away from your breaker box. So then we go down here. Okay, we're in category 2. We're going to be 240 volt. So we're in here. So we need components that can handle 2500 volts, at least for a transient. Now you might be like, my device only does 120 volts. I don't need to worry down here. I would still do the 2500 volts, just because you never know when marketing and sales is going to come around and say, hey, we don't want to sell just to the US. We want to sell to the rest of the world also. So if you can plan ahead and just get this already done, it's less work for you in the long run. So when I was trying to select components, my initial thought was, hey, let's do some 2512 resistors here, because I want to work with surface mount if possible. But it just didn't end up being that way. This is your regular run-of-the-mill 2512 resistor. And it's a pulse voltage 1700. Not cool. That's below 2500. And even if you go to like some fancy pulse proof, high power, excellent pulse load capability, yeah. Even if you do that, same voltage or same pulse voltage. So unfortunately, surface mount ain't gonna do it. So, and that's really common for AC stuff where you just have to go through hole. It's fine. So if we look at this, we go 100 ohm, and then all I did was search for pulse withstanding. All the other stuff is fine, but the pulse withstanding is what I wanted. So first data sheet we're going to look at is this guy, buddy, down here. That's 3 watts and 5 and 7. So if we look at their pulse voltages for 3, 1500, no good. 5, 2000, better, but not quite. And then 7, 3400. Okay, all right, cool, that'll work. But just notice 7 watts. If you go all the way over here, this thing is an inch long. Like that's a very big component. Now, if we look at this guy down here, a little bit different. If we look at that data sheet, oh, wrong one. It's this guy right here. See, looks a lot different. Resistance value is going to be 100. peak pulse voltage measured in kV, 4 kV. Cool. How big is that component though? Still half an inch. So I would make sure your footprints are good. That way you can handle all of these. Never single source a component. I tell people that at work all the time, man. It grinds my gears like none other. When some designer comes in, all right, got my schematic, got my layout. Oh, how many components did you spec? One. Like, don't single source, guys. It makes everybody's life a nightmare in the beginning. But, okay, so we need a through-hole pulse withstanding resistor. So this is a way different than what you would normally pick, but it's what we got to do. Now, that covers the resistor. Now we need to cover this bad boy. This is also going to be much, much different and also through hole. So what we're going to look for is a class X capacitor. So we can read a little bit of this here, but point being, commonly called as line-to-line or across-the-line capacitors. Important part, they are designed to fail short circuit in order to trigger the circuit breaker or fuse to break the supply circuit. So this is a safety thing, so we got to do it. So, okay, now we want an X2 class capacitor, peak voltage pulse equal or less than 2.5 kV, which is what we need. So this one's so much easier to look for. So if you look at ratings on DigiKey, X2. All right, cool, done. 58 cents, and it's quite large. So that covers what we need to do there. So as far as layout goes, these just need to be close to the contacts. That's it. A mistake I have seen made with how these connections are. So especially if this is soldered, especially if this is going to be soldered in, don't put it super close to the relay. Think about the poor soul that has to solder a wire to this connection. So if it's too close, they're going to gouge the relay with their soldering iron. So don't do that. Make sure it's all far away from your other stuff. That way we don't start gouging components. Don't want that. So now we're talking about layout. We're gonna also talk about what to do layout for the actual relay itself. Nobody talks about this. This is actually a bigger deal than you would let on. So just think about your relay for a second. So here, let's zoom out on this. Where does the heat go? We've got a coil here. And then these contacts here, I mean, there's resistance. Look at the data sheet. They'll give you a value. So you've got I squared R going on here. There's heat going on. Where does it go? So it can radiate through the case, but it's a sealed case, so it's really not going to do a whole lot for dissipating heat. So it's the actual pins that it goes out on. So they don't really talk about that a lot, but it does make sense if you think about it. I mean, the pins are made of metal, so it conducts heat a lot better. Okay, cool. So we're going to enlarge this right here. So you just want a big copper pore, not only on the contact, but on the coil leads themselves. So it seems Omron's the only person I can find that actually gives you like a good layout of what to do. And I had to go digging for this, guys. This is not commonly known. So you want, and they make kind of a big deal out of it. I mean, here, if we go up here, look at this. Generated heat, high. Then we want to do some cool stuff and go low. All right. Nice. So other things that are kind of beyond the scope of this video is how to do creepage and clearances and all that with AC. Just there's all kinds of rules, regulations, compliance guidelines. So just keep all that in mind, that they do exist. So now that we have covered what to do on the coil side and the contact side, this should make your relay last much, much longer than normal. So what I would encourage you to do, if you haven't already seen it, go back to part 1 where we talk about this. So I think you'll enjoy that. So please let me know what you think about this. Yeah, leave a comment. Thank you so much. Goodbye.